First question, it's just talking about laptops. So we have a class of 22 students, and each student uses, I should say that the green highlighted stuff is like stuff that's specific to the question, and the yellow stuff is stuff that you should look for generally in all questions, and stuff like they might trick you on. So back to the laptops. So each student only uses one, and the probability that it's not correctly plugged in, so I'll call that not plugged in. Plugged in is 0.1%. I mean 0.1 because it's 10%, and it's one student is independent of the other student. So we're looking for the probability at least one not correctly plugged in, so not correct. You can just put that into your CAS, or you can just do 1 minus probability none incorrect. Since we have a CAS, it doesn't really matter which way you do it. This would simplify to 0.9 to the 22, which is 0.9015. As you can see, this question is binomial. Usually if a question doesn't state specifically that it's continuous probability, then you can kind of assume it's binomial. But also with the question, it mentions, you can see the one probability is that it's plugged in properly, and the other one's that it's not. So you can kind of tell. So next question is a given question. So the red highlighted it red here because even if it didn't have the given part, you would be expected to realize that this statement above is the given part. So they didn't trick us in this question, but they could have. So I'll, since we haven't defined a variable, I'll let x equal amount incorrectly plugged in. So now we're trying to find the probability that there's less than 5, given that there's at least one that's not correctly plugged in. So we know if we expand the given function, it's x is less than or equal to 4. So again, since we have we're using binomial, you always want to convert inequalities that don't have an equal sign to inequalities that do, because there's just less of a chance that you might put something wrong into your calculator. So this is then the probability that x is between 1 and 4, both inclusive, which is what we want, over the probability that x is greater than 1, and just put that into your CAS, and you should get 0.9311. So now they're specifically saying that we're moving on to normal distribution, and they've given us a mean and a standard deviation, and they remain out of the charging trolley for 3 hours. So that's how much they're going to need before it can go back to charging. So find the probability that it will stop working by the end. So if it's by the end, that means we want the probability that x, I'll call it B for battery life. You'd probably want to define this as well. Is less than 180, because you want it to die before the 3 hours up. So again, you could just put this into your CAS, where the mean is 3 hours and 10 minutes. So you want to convert this to minutes because everything else is in minutes, or maybe not everything else, but you can't use decimals because that would be not as precise, especially given that it's it would be 1 on 6, so 3 plus 1 on 6 hours. So the best thing to use would be minutes, especially given that standard deviation is also in minutes. So the lowest common unit, I guess. So mean is 3 hours and 10 minutes, which is 190 minutes. And standard deviation is just 6 minutes, and put that into your CAS, and you should get 0.0478. So now we're moving on to sampling, and we want the probability that it's greater than, p hat is greater than 0.06, given that it's greater than 0.05. So you can either start by converting this to the normal distribution, or you can start by expanding the given sign. I'll just start by expanding the given sign. So the intersection of these would just be that it's greater than or equal to 0.06, and then over the given, which is greater than or equal to 0.05. And then we know we have to convert it to x, because we can't find probability if it's in terms of p. So x is n times p, and n is 100, so if we just multiply both the values by 100, we get x is greater than or equal to 6 on x is greater than or equal to 5. And since it's saying do not use normal approximation here, that's important. That means we have to go back to binomial distribution, and it just affects what function you put into your CAS. But basically, you want to solve for this in your CAS, where n is 100 and p is 0.0478. If you're wondering where we got the p-value from, it's actually from here, because this is talking about the amount of laptops that will die. We have a battery life of less than 3 hours. So the amount that will die before they can be recharged. So that's why you use your p-value from the previous question here. So yeah, you just put that into your CAS and you should get 0.658. Just be careful that they've changed the amount of decimal places required. So now the battery life was back to normal distribution here, because we had to go to discrete in the previous question, but now we're back. So that's why it's important to read the question a bit. But the mean battery life has changed to 3 hours, and the probability that a laptop works for more than 3 hours and 10 minutes is 0.12. So first we'll just write down the information that we know. So the probability that battery life is greater than 190 is 0.12, and the mean is 3 hours, so it's 180 minutes. And now we're trying to find the standard deviation for the battery life, which have been used. So anytime we're trying to find standard deviation or mean, then the one thing we can rely on is standard normal distribution. So we're going to have to find the z value, which gives the same probability. In this case, you just use your inverse normal function on your CAS, and the default settings are set to standard normal, so you don't have to change any of those. And you should get this value. I got 1.174986. And then you just convert it to x. So 1.174986 equals 190 minus mu, which is 180 on sigma, because sigma is what we're trying to find. And then sigma is just 10 on this value, and that simplifies to 8.5107 to 4 decimal places. The changing decimal places might trick you, just be careful. So now we have a sample of 100 laptops again, and we're back to sampling. So suppose that they're testing it one at a time. So that's a hidden replaced. That means like that the laptop's taken and then it's returned to the sample size. So if we have a sample size of 100, and the probability, so if it's less than 3 hours, if you remember from the previous question, 3 hours is actually the mean, and it's normal distribution. So in normal distribution, anything that's like one less than the mean or greater than the mean, it's going to be half. So the probability that the battery life is less than 180 minutes or 3 hours is half. And then find the probability of the first laptop to have a battery life of less than 3 hours is the third one. So probability third one, less than 180 minutes. So the first two, we want to have more than 3 hours. So if you think about it, if less than 3 hours is a half, then more than 3 hours is going to be 1 minus a half, which is still a half. So probability battery life is greater than 180 is a half. So the first one we want to be greater than 180, so it's a half, and then the second one same, and the third one same. Doesn't really matter because all of the probability values are the same, but you should get 1/8. So now we're looking at a 95% confidence interval. So we know that n is 100, and 6 of them, so if 6 of them have a battery life of less than 3 hours in a sample size of 100, that means the proportion is 6 on 100, and we need that because we're talking about the proportion. So this is also sampling proportion. So proportion is how many affected individuals or objects there are in the total population. So proportion is 0.06, and your sea level is 0.95. And you can either do this using the formula, so p hat minus 1.96 times n p, on n, 1 minus p, and then p hat plus 1.96 times p, 1 minus p on n. Or you could just go into your CAS and use the function there, but you should get 0.01, 0.11. So that's the probability question for 2016. So in 2017, we have this one. So we have a probability density function, and they asked us to graph it. So just looking at this, you can graph it on your CAS. Either way, they're linear lines, so it's not that bad. The mean, or not the mean, sorry, so it stops at 45 and changes direction. So graph kind of looks like this. Oops. And then down to 70. But the thing to be wary of is this part of the question. Because you might draw this and think you're done, but actually you have to draw the rest of it, because for any other values of t, the probability is 0, as defined by the hybrid function. So you have to draw all 3 of these graphs. So this probability, since it's a probability density function, we just use integration between the 2 limits. So ft dt, and that's equals 4 and 5, because they, it's an exact value anyway. So now we have a given, so just expand it. It's the intersection between these 2 over the given condition. So the intersection would be just that it's less than 25 or equal to, and over that it's less than or equal to 55. And again, just use integration to find those 2 values and divide them, and you get 1 on 41. So find A such that the probability of t greater than A is 0.7. So basically what we're looking for is the integration of from 70 to A, ft dt equals 0.7. So since it's decimal places, we can use our CAS, but the only problem you might come across is the hybrid function in your CAS, because it might take a while or just might not work. So to make it easier on yourself, you can realize that up to the halfway point, 45 here. So this area is going to be half, and this area is also going to be half. So if the probability that the t value is greater than A is going to be 0.7, then you know your t value is going to be less than 45. So say it's like here somewhere, this is your, that's a pretty bad line, but this is your t equals A line. So the probability, the area under the graph to the right is equal to 0.7. So that means the area to the left is equal to 0.3. And the graph representing this left line, so this one here, is this one. So by doing this, you no longer have to deal with the hybrid function, and you can just deal with that. So for this, you would just integrate this top part. So I'll just call it f1t equals this. So you would just integrate from a to 20, f1t dt equals 0.7, and just solve for a, and she get 39.3649. And that should be much easier than trying to get the hybrid function to work on your CAS. So a equals 39.3649. So immediately you can see this question, we've moved on to binomial distribution. and it's about homework, and it's independent. So find the probability that she spends more than 50 minutes on her homework on more than 3 of the 7 randomly chosen days. So this is the probability that, say X, I'll let X be the amount of days she spends. So X is greater than 3, and we know we always want an equal sign in our equality, or so probability X is greater than or equal to 4. And you can just put that into your CAS where n equals 7, because 7 days of the week. And the P is 8 on 25, because they give that to you in the question. And this comes out to 0.1534. So find the probability that she spends more than 50 minutes on her homework at least 2 of the days, given that she spends more than 50 minutes on at least 1 of the days. So what we want to find is X is greater than 2, given that it's greater than 1. So the intersection between these two is greater than 2 or equal to, over that it's greater than or equal to 1, and simplifies to 0.7626. Just remember that it's binomial, so make sure you use the right function on your CAS. So now they've kind of taken out the numbers, but you still use the same concepts as you did before. So P's probability that she spends more than D minutes on her homework. So the probability that T, I'll say, is the time she spends on her homework, is greater than P, is greater than D, equals P. And Q is the probability that on 2 or 3 days she spends more than D minutes on her homework. So Q is a probability that T is greater than D for 2 or 3 days. So just remember that or usually means addition or union. So we're going to add 2 things together rather than multiply them. So express Q as a polynomial in terms of P. So if you ever get like a polynomial in probability, if it's a discrete probability, then you know you're going to look at your and choose X kind of equations. So Q is probability that out of 7 days she chooses 2. So probability 2, 1 minus P, probability 5. Or, so we're going to add probability that she chooses 1. Probability 3, to the power 3, 1 minus P to the power 4. And you can just simplify this on your CAS, expand it. Since it's asking for a polynomial, you can either leave it in factorized form or expanded, but you have to get rid of the combination in front of each pair, and it's probably easier to see, I guess, what's happening if you expand it, but it doesn't really matter. I think in the answers they left it as in the factorized form. That's the expanded version. So find the maximum value of Q. So you could just do Q max on your CAS, but make sure you put a domain, because we know that P has to be an element of 0 to 1, because we know it can't, because we know it can't be greater than 1 and can't be less than 0. And when you do that, you should just get Q is 0.5665, and when P is 0.3, P is 0.3539. So now we need to find the value of D. So as we said before, the probability that T is less than D is P, which we now know is 0.3539. And if we remember from our T, the way we figure out what the probability is, we use this hybrid function. So this question here, whether asking us to find D, is the same exact question as when they asked us to find A. except the probability values changed. But this time, since the p-value is less than 0.5, sorry, then you know that, but this time it's the probability that t is less than d. So since the probability is less than 0.5, then d is still going to be, it's the other way, sorry. So for this one, we were looking at t is greater than a, and for this one, we're looking at probability that t is less than d. So this is going to be 70 to d ft dt equals 0.3539. And since, you could just solve it in your CAS because you have everything. Make sure you use the hybrid function and do the same thing as before to avoid your CAS not working. Just that trick is just like using geometry to make it easier for yourself. And you get d is 49 to the nearest minute. So that is 2017. So, yep. So 2018 question. Doctors are studying resting heart rate of adults in Matsland. So this is the question. There was actually, I don't remember which NHT paper it was, but I'm pretty sure it was like the exact same as this question. So just something to note, I guess. So find probability that a heart rate is between 60 and 90. So X, I'll just let X be the heart rate. So between X, this, and using normal distribution. I forgot to highlight that. Normal distribution on your CAS, you get 0.838. 838. So slow heart rate is when it's less than 60, and probability that someone has a slow heart rate is this. And 29% of people play sport, and 9% play sport and slow heart rate. So as opposed to the other question where we had or, which was plus, we have and. So this is multiplication or intersection, whereas this one was union. So random selected adult plays sport regularly. H is slow heart rate. So find the probability that H given S. So we want the probability that H is intersection S over the probability that S happens. So H intersection we got from here. So remember the and is intersection, so it's just 0.09. And the probability that someone has a slow heart rate is, S is sport. So 0.29. So there we go, and we just chuck that into a CAS. And I think it's exactly 0.31910. So are H and S independent? So we know if they're independent, then probability H times probability of S equals probability of H intersection S. So in this case, intersection S is 0.09, and probability of H times probability of S, so that's 0.1587 times 0.29. You actually get 0.04023, which is not equal to 0.9. So we know that they're not independent because this doesn't hold true. So since probability H times probability of S does not equal maybe it's better to write does not equal probability of H intersection S, they are not independent. So find probability in sample of 16, that there's exactly one person with a slow heart rate. So for this one, we want probability that 1 in 16 will have a slow heart rate. So now we've moved on to binomial distribution sampling. So find the probability that p hat is greater than 10%, so greater than 0.1. But we know we can't find probability in terms of p hat, so we have to convert this to x. So to convert it to x, we just multiply by the sample size. So x is p times n, which is 0.1 times 16, which is 1.6. So now we have, this is the same as probability that x is greater than 1.6. But since we're dealing with binomial distribution, you can't have 1/6 of a person, and we also want an inequality that has an equal sign. So if you consider a little number line here, so 1.6 is here, 2 is here, 1 is here. So we want x is greater than this. But since we want a whole number, we're going to move to the next closest thing, which is probability that x is greater than 2. Or greater than or equal to 2, sorry. Greater than or equal to 2. And you could just chuck that into your CAS using binomial distribution. 2, and you should get 0.747. So for a random sample, we want the least value for which this is true. So again, it's the same step as the other one, except we kind of have a variable now because we don't know what n is. But first we have to convert everything to x because we can't find probability in terms of p hat. So we just multiply by n, but in this case you can see multiplying by n will just give you 1. So this is equal to probability that x is greater than 1, which is greater than 0.99. And again, we want to convert this to equal sign. So probably x greater than or equal to 2 is greater than 0.99. And if you think about the number line again, so we're dealing with the same probability actually. So this goes on infinitely, but this one stops at 0. So if you think about it, if we're trying to find this probability, we're actually going to need the sample size because the endpoint here will be the sample size. So it'll be n. So it'll go from n to 2. So we'll need a sample size in our calculation. But if you look at the probability of from 1 to 0, which is 1 minus this probability here, you actually don't need the sample size because you're just going from 0 to 1. So this would be the more favorable option to use because you use n just as a sample size and not actually as one of the boundaries. So to do that, we're just going to make this 1 minus probability that x is less than 1, less than or equal to 1, which is 0.99. And then if it's less than or equal to 1, that means it's either 1 or 0. So x is equal to 1 or it's equal to 0, which is greater than 0.99. And then you just have to expand everything using binomial distribution. So we have n choose 1, p1, 1 minus pn, and then minus n choose 0, p0, which is 1 minus pn. So less than 0.99. Okay, so you could do this algebraically using this method, but also, as I said before, there's that option in, so first you go into your main menu. So in main, you use your binomial CDF, and you go all the way back to this step here, and you just put in the thing as you would normally. So lower bound 2, upper bound, we'll call it x, and then x trials as well. And the probability This is about slow heart rate. So the probability is 0.1587. So, and then the probability is 0.1587. And you just press enter on this. So this would be like binomial CDF or something. And then it'll give you an error. But regardless of the error, just copy and paste this entire block into your graphing menu. So the one that's like y equals something, just paste this there. And then get rid of the graphing menu that looks like this. And instead in the top button, the top bar, you'll have a thing that looks like a table. And you click on that one, and it'll actually have like a list of probability values and a list of n values. So because it will treat n as x, which is a variable, and then it'll give you a probability value based on that. And for this particular question, all you do is look for the n value that's just greater than 0.99. So like it'll have like n is 1, n is 2, 3, 4, infinity, and it'll have infinity values here. And that's easier than doing this algebraic method. You could do it this way, but your CAS might stop working, so this is probably the best way to do it. So yeah, just use your graphing menu for this question and use the table function. And when you look at the list of values, you'll see that the closest n value that's greater than 0.99 is 39. Sorry, this is n equals 39. So we're doing confidence interval now, and sample proportion. So sample proportion we know is the middle value of these two. So P is just going to be 0.102 plus 0.145 divided by 2, which is 0.1235. So explain why confidence intervals suggest that proportion of adults are slow could be different from in maths land. So if you remember from the NHT paper, so basically all you have to do is point out that this value here, 0.187, is not a part of this interval here. So so the other one was 0.1587, I think. So you can clearly see that's not a part of this interval. So all you have to say is probability, maybe just write probability H equals 0.1587 in Mathsland, which is not included in the 95% confidence interval of 0.102 to 0.145. And that's all you have to say. You just have to point out that that value is not actually in the confidence interval. You didn't actually have to get any of these questions right to get that one right, so it's kind of like 3 marks. So now we've moved on to a probability density function to find the expected time. So expected time is just integration from the domain, which in this case is infinity to 0 t times the function dt, and chuck that into your CAS and you should get 44.6 minutes. So elite students are those who can take less than 15 minutes to do this. So find probability someone's elite. So probability elite is less than 15, so 0 to 15 mt dt, and chuck it into your CAS and you get 0.266. So now we have moved on to binomial. So we have two things here. So we have you're either a year 12 student or you're not, and you're either elite or not. So to help me understand, I kind of drew a tree diagram. So the first thing is whether you're year 12 or not, And the second thing is whether you're elite or not. So elite, not elite. So year 12 students make up a seventh of the score. So probability that someone's in year 12 is 1/7. So the probability they're not year 12 is 6/7. And of the year 12 students, 0.5 are elite. So elite is 1 on 20. So not elite is 19 on 20. And then we're trying to find the probability that a non-year 12 student is elite. So we're actually trying to find the end probability of this branch, not this branch, this branch here. So this value times this value is going to give us a value here. And this is the one we're after. So to find this value, we clearly need to find this one first. And the way to do that is we actually have the probability that someone can be elite because we figured it out here. Here. So the total probability that somebody is elite, so probability elite is this branch plus this branch. So we have, oh, sorry, we are not looking for this, we're looking for this, the star. So we have the addition of these two branches gives us elite, which we found is 0.0266. So this is 1 on 20 times 1 on 7 plus 6 on 7 times the one that we're after. I'll just call it x. And as you can see, we only have one unknown. So you can just chuck this into your CAS and you get x is 0.0227. So the probability that you're not in year 12 and elite, which is what they're asking for, is 0.0227. So that was the 2018 question. So the 2019 question, so find the mean life. So the mean, again, is just I'll call it EX. Integration from the domain, which is 5 to 0 in this case, of x times the function, dx. And since it doesn't specify decimal points, we have to give exact value. So 10 on 3 weeks. So now we have a sample of 80, and how many are expected to live longer than 2 weeks? So so this is kind of where you use, so expected, it kind of means expected value. So we're going to use mu is n times p. We're like shifting between the probability density function and binomial distribution right now. But first we have to do how many of them, like what's the probability that they'll live longer than 2 weeks. So the probability that x is greater than 2 is integration between 5 and 2 of fx dx, which is 2853 on 3125. So the expected value longer than 2 weeks is going to be n times p. So this 80 times this value here, I'll just call it p. And the closest integer is 73 because you can't have a decimal value of a living thing. So what's probably that something, the butterfly lives for at least 4 weeks, given that it lives for at least 2 weeks? So looking for probably that x is greater than or equal to 4, given that it's greater than or equal to 2. So the intersection would just be greater than or equal to 4 over the given. And yeah, just use integration to solve this part and this part, and you should get 0.2878. So now we're moving on to normal distribution, and they give us the mean and standard deviation. So find the probability that it has a wingspan between 16 and 18. So probability that it's between 18 and 16. It's just the easy CAS question. Comes out to 0.1512. So now they're saying if it's very small, then it's in the smallest 0.5% of all of the birds. So it's basically saying that the probability that the wingspan which I should probably call, I'll call it W, sorry, because the other variable was X, and we don't want to get confused. So probability that W is less than a value, I'll call it A, is going to be 0.05, and A is the maximum wingspan one can have for them to be considered very small. So we're trying to find A, and since we know the mean and standard deviation, we don't have to use standard normal distribution. You can just use inverse norm CDF. I think it's called in the CAS, using here and using the left tail, because we're looking for the probability that of this one is less than A, so the tail is to the left. So it's fine for both the CASs because the black one's automatically set to left. And yeah, you just solve for A and you should get 10.6 to the nearest one decimal place. When you're deciding whether to round it up or down, make sure you consider that it's in the smallest 0.05 percent. So since it's not an inequality, I guess it doesn't really matter, but like if it had said like less than or something, then just that's how you would decide whether to round up or down. So next part is that there's a sample of 76, and now they're very large if it's greater than 17.5. So and now they've given us the probability that it's large as well. So find the probability that in a sample of 36 that 3 or more are large. So probability that I'll call them B for butterflies, amount of butterflies, is 3 or more. So including 3, at least 3. So 3 or more into your CAS. But this time it's binomial, so be careful of what function you use on your CAS, and you should get 0.2947. So now they're telling us the probability that the butterflies is greater than or equal to n in a sample of 36 is less than 0.01, so less than 1%. And they're asking us to find n. So as in the previous question, here where I mentioned that it'd be easier to use 1 minus than this one because you want to get rid of maximum use of n, so you could do it like that. But also, I think this question was only like 2 marks, so as long as you state this and then state the p-value you're going to use, which is 0.0527, you can use that same trick in the graphing menu where you just put in your normal binomial CDF as you would, get the arrow function, and then copy that function into your CAS and just check for the closest n value that's less than 0.01. And you should get 7 because the only way you can really do this question is by trial and error. So the graphing menu kind of helps you take away the this one. We're moving on to sampling now. So find the expected value and standard deviation. So we know in sampling the expected value, which is mu, is p. In this case is 0.0527 because they gave that to us here. Standard deviation is square root of p1 minus p on n. So p is this one and n is 36 because that's also given in the question. And if you put that into your CAS to 4 decimal places, standard deviation is 0.0372. So no tricks here, you just use the formulas. So what's probability that the sample proportion lies within one standard deviation of 0.0527 and saying do not use normal approximation. So if it's saying do not use normal approximation, the only other thing we can use is binomial. So that's just something to keep in mind. Doesn't really affect how you do the question, but it affects what function you put into your CAS. So we're trying to find the probability that it's one standard deviation of away from 0.0527. So it's going to be one standard deviation less and one standard deviation more. And we found in this question that this is the standard deviation. So if you just plug that in, you get probability that p hat is between 0.01546 approximately and 0.0899389. But as we know, we cannot find probability if it's in terms of p hat. So we have to convert this to x. So to convert it to x, we multiply it. X is n times p. So we multiply both of these values by the sample size, which is 36. And then you should get the probability that x is between 0.55654 and sorry, my pen refuses to erase. And 3.337. So since it's binomial, we have to convert these to whole numbers because you can't have a fraction of a butterfly. So if you think about a number line again, so we have 0.55 something here, 1, 0, we have 3, 3.37, and we have 4. So currently our x is between these two values. So the closest whole numbers that give us a subset of these is between 1 and 3. So this is the same as probability that it's between, that x is between 1 and 3. And you should put this in your CAS where n is 36 and p is 0.0527. And you should get 0.7380. So we have 95% confidence interval for the proportion. So we're still in sampling, and it's calculated to be this. Find the sample size. So to find sample size, it's best to find the p-value first. And we know the p-value is the middle value of these two numbers. So just add them together and divide by 2, and you should get 0.055. And then it's really, you can choose your lower or higher, lower bound or upper bound, and just use the formula that you would use to find that value. So if we're using the lower bound, it's going to be p hat minus 1.96 times p1 minus p on n, which is equal to 0.0234. And then let p equal 0.055 and solve for n. And to the closest whole number, because again, we're dealing with butterflies, so we need a whole number, n is 200. Just be careful in other questions, they might not use a 95% confidence interval. So depending on what the confidence level is, the z value is going to change. So just be careful of that. It's not always going to be 1.96. So that's the 2019 question. So 2020. So now we have some normal distribution, as you can see, but the mean is 0 and we have a standard deviation of 4. So find probability that t is less than a to equals 0.06. I mean, just 0.6. So since we have mu and sigma, we don't have to use standard normal distribution. We don't have to worry about z at all. And you can just use inverse norm CDF on your CAS, and the tail setting should be left. Because as you can see, it's less than a, so we have like a here somewhere. We're going to use the left part of the tail. That's why the CAS setting is left. But yeah, you just do that and you get to the nearest minute, it's going to be 1 minute. So find probability that a delivery is no later than 3 minutes, given that it arrives late, so it arrives after its scheduled time. So if it's no later than 3 minutes, then t is less than 3. But in this case, since it's later than 3 minutes, then it's going to be negative, because to the left of 0 is late. So if it's no later than 3 minutes, that means it's 3 minutes late or less than that. So it's going to be from here to here. Oh, so actually it's going to be from here all the way to here, because if it's no later than 3 minutes, that means it might arrive on time or even earlier. So we have t is greater than or equal to -3, given that t is less than 0. T is less than 0 because if it's arriving after its scheduled delivery time, then it's going to be late. And if it's late, then the time is going to be negative. So our intersection for these two is that t is between -3 and 0 over the given condition, which is that it's late. And if you put that into your CAS using normal distribution, you get 0.547. So we're given that a transport company can make 46.48 of its deliveries in this interval. And the mean is now k, and standard deviation of 4 minutes is the same. And the thing to note here is that we're using the same model. So all they've done is that they've changed mu to k, but they've kept this graph the same. Because we know in our normal distribution graph, k is going to be x translation. So the only thing that's happened is that they moved this graph either to the left or the right, depending on what k is. And now they're trying to find k values. If the same probability between -3 and 2, so between here, we're given this probability is the same, except now it's between -4.5 and 0.5. So basically, we're trying to find the x translation of the graph that caused this. So this is actually kind of like those multiple choice questions. It's kind of like that, where you just have to find like you're converting between x and z, except this time you're converting between x and x, and the k value, which is mu, is the one that's changed. So if you think about the original function, its mu was at 0, and the probability that we're looking for is between -3 and 2. So the first thing we know is that the probability between -3 and 2 is the same as the probability between -2 and 3. And the second thing we know is that this mu function, we don't know what k is. So I'll just leave it like this because we don't know where it is. But now the probability between -4.5 and 0.5 is the same. And we want to find how much we've moved k. So like in this diagram, it's where we've moved this y-axis. So you can see that the -3 terminal has become -4.5, and the 2 terminal has become 0.5. So you can easily see that the x translation that's occurred is that they've moved it to the left by 1.5. So one value of k you've already gotten just by looking at these graphs, and the endpoints is that k is -1.5. So one is that you've moved it to the left. But if you read the question, it's asking for multiple values of k. So once you get this value, you always have to look for another one. And then that's where this symmetry property comes in handy, because now you can see that, sorry, this should be a 3. So not only has the original boundary from -3 to 2 gone to -4.5 to 0.5, but this should be the same as -2 to 3, also going from that to -4.5 to 0.5. So we have another k translation here, but this time it's -2.5 if you compare the values. So our second k value is -2.5, and just generally checking whether they meet the criteria. So yep, they're correct to 1 decimal place. And so yep, that's it. The 46.48 is a complete distraction. You don't need this number at all. It's just there to show that these two areas are the same, but the actual number doesn't matter. They could have said 0.01 or anything. They could have even just given you like a letter and not an actual number, but it wouldn't have mattered. You would do it the same way. So now they're changing the company. So there's a rival company, and this is 0.585, probability that things arrive earlier. We have independency, and we're assuming that the claim is true. So find the probability that it makes 8 deliveries and fewer than half of them arrive on time or earlier. So this is binomial distribution because we have that either it arrives on time or it doesn't. So probability that it's on time is 0.85. Oops, 85. So the probability less than half of 8 arrives on time or earlier. So that's either none of them, one of them, 2 of them, or 3 of them. We don't include the half because it's less than half, so that's not including 4. It's just up to 3. And then you could just use your CAS to simplify this. You don't even have to write this out. You could just do 0 to 3. And that comes out to 0.03. So now they're making n deliveries. So they're taking out the letter. So express in n the one or more the probability that one or more deliveries will not arrive on time or earlier. So probability that one or more deliveries, so x is greater than or equal to 1, will not arrive on time or earlier. So not arrive means we can't use the 0.85 because that's the probability that it will arrive on time. So at least one not on time is x is greater than or equal to 1. But because we don't know n, so kind of like instead of doing like with the timeline before where you have that interval from here to here, which is like n, or you just have from 0 to the value before. It's always easier to choose from 0 to the value that you want it to be greater than, because then you don't have n twice. So we're going to change this to 1 minus the probability that all of them arrive early. So all early. So that's going to be 1 minus 0.85 to the power n. And that's the easiest way to do the question, because otherwise you'd have to use, so probability that it's 1 to a, but when you're expanding it from like n choose 1 and then n choose 2, like you wouldn't know where to stop because you would have to keep going like until you reach n, which you don't know what that is, so you can't do it that way. So find the minimum value of n such that there is at least a 0.95 probability. So now we're looking for the function that we figured out in the previous question, but we want it to be at least 0.95. So we want it to be 0.95 or greater. And you can just solve for this on your CAS, and you should get n is 19, but just be careful with the rounding. I think in this question we had to round down because just because it's like 18 point, I don't know, maybe it's like 19.5 or something, doesn't mean you should always round up. Especially in probability, you always want to check one up and one down to check if it satisfies the inequality. Or you could just solve it with the inequality instead of equals. Like it's usually easier to put like solve for something equals blah 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 instead of greater than or equals, because sometimes this takes more time on the CAS. But if you put it as straight up like this in your CAS, then it won't. You don't have to check whether it's up or down because your CAS will tell you. So now there's the government is getting involved, and the probability of arriving on time or earlier is between 0.3 and 0.7. So now they believe that the probability of arriving on time is actually 0.75. So that's less than what they originally said, which was 0.85. And now we want to find the minimum and maximum values of y. Maximum values of y. So like the year 12 question in the previous part, there's two things to this. So there's either that it arrives after 4 p.m. or it doesn't. And then it's either arrives on time, so on time or not on time. And we're trying to find why. So we'll just fill it in with the things that we know first. So the probability that arrives if it's made after 4 p.m., then the probability that arrives on time is x. So this is x, and then this is 1 minus x. And then the probability that it's made after 4 p.m. is y. So this is y, 1 minus y. And this one, these two values we actually know. This is 0.75, and this is this is not 0.75. If it's not 4 p.m., we actually don't know what these two values are, but no, we do. Like I said, these values are from the previous question, from here. So, because this is about, so they've not actually changed the value. This is the overall probability, but we're still dealing with this is before 4 p.m., so we can keep the 0.85 value. So, because it says up here that the analysts, where is it? So the analyst's claims is only true for deliveries made before 4 p.m. So we can use the company's claims before 4 p.m. So the company claimed that it was 0.85. So we can use that value here, 0.15. So now we know the probability that something is on time. So on time is just t, is 0.75, which they've given here. So 0.75, so that if we look at the tree diagram, that's going to be this branch and it's going to be this branch. So y times x plus 1 minus y, so that's y dash times 0.85 equals 0.75. So if we expand this, y x plus 0.85 minus 0.85y equals 0.75. Oh, I forgot the y. So if we factor out the y, we get x minus 0.85 and negative 0.1 on this side. And since we're trying to find the minimum and maximum values of y, you can kind of see that we're getting it into a function of where x is the independent variable and y is the dependent variable. So now we have a truncus function. And just like we would in normal questions, to find y max, we just enter this into your CAS. But be careful because they've given you a domain of x. So x is an element of 0.3 to 0.7. So 0.7. So just put that into your CAS and you should get y max is when x is 0.7 and the maximum is 2 and 3, and the minimum is 2 and 11. If you ever want to double check your answers, just consider the the truncus function that we got. So it was negative 0.1 on x minus, so that would be the asymptote, and then the graph would look something like this. So we know x is valid from 0.7 to 0.3, so it'd be like 0.3 here, 0.7. So we're just looking at here. So we would expect our minimum to be at 0.3 and our maximum to be at 0.7. And that makes sense because when you're checking these values, your CAS will tell you that holds true. So you can be sure that your answer is correct. And that's your probability question for 2020. And that's it.